In this episode, you're going to learn about big O notation. You use big O notation to describe the efficiency of data structures and algorithms in a concise and consistent way. The efficiency of a program is not based on time. The time for a program to complete a specific task is affected by where you decide to run your code. The more powerful the computer, the less time it will take to complete a task. So, time is not a consistent measure of efficiency for algorithms. To measure efficiency, a consistent measure would be the number of steps the program will take to complete a task. The number of steps an algorithm takes will always be the same, regardless of how powerful the computer you choose to run your code. Programs are created to work with data, and the number of steps to complete a task is determined by the algorithms you use to operate on data in your programs. To analyze the efficiency of algorithms using Big O, you have to imagine how the number of steps grow as the data increases to infinity. Seeing how the number of steps grow as input data increases is a measure of efficiency known as time complexity. Let's look at a few scenarios to understand how to analyze time complexity. What would be the time complexity for writing a program to get the value at a specific index in an array? The computer has the ability to go read the value at any index of an array in a single step. No matter how large the array is, it will still just be a single step because it has the ability to instantly read any memory address. So the size of the array doesn't affect the efficiency of reading an element in a given index. Since the number of steps remain constant regardless of the size of the data, the time complexity for this operation is O of 1, which is known as constant time. Next, let's imagine searching through an array using the linear search algorithm, which is just searching through an array one element at a time. As the number of elements grow towards infinity, the number of steps to complete search also grows proportionally. So using Big O notation, to communicate the time complexity for linear search, we would just say that it's O of n. Algorithms with an efficiency of O of n means that for every data element added, the number of steps also increase by the same amount. This is why O of n is also known as linear time. Just for a moment, imagine that the value we're searching for happens to be the very first element in the array. This would be the best case scenario. Then technically, the time complexity could have been O of 1. But when it comes to Big O, what matters more is the worst case scenario, because understanding the efficiency of an algorithm in a worst case allows us to make informed decisions about mitigating potential problems that may arise in the future. Next, let's analyze the time complexity of searching through a sorted array using the binary search algorithm. With binary search, we don't have to search through all the elements in the array. If we imagine the array size increase to infinity, we notice that every time the data doubles in size, the number of steps increase by just 1. The time complexity for such an algorithm is known as log time. In Big O, we express this as O log of n. Now that you have some idea about Big O, let's look at some concrete examples using the rules of Big O to help compute time complexities. So here, you have a function called example1 with an input n. The only part of the code that is dependent on the input data is the for loop. The for loop step will execute as many times as specified by n. So this function executes n steps incrementing the counter by 1, and then an additional step to increase the value of the counter by 10. Following the coefficient rule, you eliminate any constant step, so the plus 1 gets ignored. The plus 1 is negligible when the value of n goes to infinity, so the time complexity of this function using Big O notation is expressed as O of n. In this example, we have two for loops that's affected by the input data n. The first for loop is n steps long, and the second for loop will have 7 times n steps. The sum rule says that the time complexities can be added. So the total time complexity is n plus 7n, which is 8n. Now we can apply the coefficient rule to eliminate any constants. So the final time complexity expressed in Big O is O of n. To wrap up, I'll conclude with an example demonstrating the product rule. So in this function, the piece of code affected by the input data is the nested for loop. The Big O product rule says that you can multiply time complexities together. outer for loop has a time complexity of n. The inner for loop has a time complexity of 7n. The nested for loop as a whole has a time complexity of n times 7n, which is 7n squared. Now you can apply the coefficient rule to eliminate constants, and you're simply left with n squared, which is quadratic time. At this point, I think it's safe to leave the other rules for you to look into on your own now that you have a good understanding of big O and time complexities. And if you found this video helpful, please subscribe to my channel, hit the like button, and I'll see you in the next one.